Hello everyone, so welcome to today's lecture. So in this lecture, we want to continue our introduction of relations. So in last lecture, we already introduced what is a relations. So actually this is a subset of the product of the two sides. And also we introduced two important type of the relations. They are the reflexive relations and also symmetric relations. So today we want to continue our introduction of relations. So the first one I want to introduce today is about the anti-symmetric relations. Okay, so for anti-symmetric relations, this means again we have a relation denoted by R, and we say this is a relation of our R of subset of A times A. Then what is an anti-symmetric relation? It means if we have a pair of AB in our relation and also the flip of them, BA also in this relation, then we will find the value of A and B should be exactly same. Okay, so this was the definition for our anti-symmetric relation. And also, of course, we can write it as what we learned in the quantifier, universal quantifier, and the symbol of sign and logic operators. So here you can see we can write it as for every AB, if we have this condition, this is our hypothesis, which means AB in our R and BA in our R. So means AB is a element in our relation and BA is also an element in the relation, then we can get a conclusion that A, B is equal to each other. Okay, so I understand this one is kind of abstract. So let's look at some example to explain this. So here for this one, the first example is this. So here we have three relations, and again, same with our previous one. For this, we also have our side A is equal our R, so which is our real number side. Okay, so now for all the real numbers, for R1, our first relation, this is defined as A smaller or equal to B. So this is our relation. So this relation is smaller or equal to B. Smaller So based on this one, what we can have is we need to find a pair of AB which is in this relation, and then we will try to find is this flip of them. So it means BA is also in this relation or not. So let's try to look at this. So here, let's think about what is a pair of AB in this relation. So here for this, what we have. So we can think about any number, real number smaller than the other one. So for example, if we think about A equal, for example, maybe 1 and B equal another value, so maybe 2, then we will have value of A is smaller than value of B. Okay. However, when we check about the flip of them, like this means BA, then we will find actually BA is not in our relation because we won't have 2 is smaller smaller than or equal to 1, right? So that means for this one, although we have AB in R, but we won't have BA in R, so in R1. So that means this is not what we need. Example to check the anti-relation here. Okay. So then what we should do is we need to find something like when we flip this two value, it's still in our relation R1. So that means think about what we can have. If we even flip this to value AB, they still have the other B, the value of B is still smaller than A. So everything we can think about is if A, B are equal each other. So that means only when value of A and B are equal each other, we will have this flip of them is still in our relation. So only when the value of A equal B. Okay. So this is the only case we can have A smaller or equal to B, which is holds at the same time B smaller or equal to A is also correct. That's the only case. So this is why we say actually for this example, our R1, we will have this is an anti-symmetric relation here. Okay, and then let's look at the next one. So for the next one, what we have this relation is smaller than. So for this smaller than, then let's think about the example that think of is A greater than, so A is greater than B. So for this one, if we think about this, so whenever we find a value of A which is greater than B, actually what we have, we will find if the value of A is greater than B, then we never have any flip of AB, like B will never greater than A, because like 2 greater than 1, we never have the flip of AB like 1 is greater than 2. This is impossible, right? So that means for our R2, actually we cannot find any pair of AB which have AB in our R2 and also BA in R2. So in this case, because we cannot find any hypothesis for our definition here, so here all of this hypothesis here for our condition relationship is false. So as what we learn in the logical operator, we know if the hypothesis is always false, then this conditionals, false implies no matter true or false, it always give us condition as true. So that means here, because we can't find any AB in R2 and also BA in R2, so that means the hypothesis is always false. So what we can have, we have the conditions is always true. And because the conditions is always true, what we have, it means for this one, we will have this is satisfies the definition of anti-symmetric. So this is also a anti-symmetric relation here. Okay, so this is because we never can find. Maybe let's type it here. So we cannot find any AB and also BA in this relation. So the hypothesis is always false. Then the conditional is always true. So the definition also, so this relation satisfies the definition of anti-symmetric relation. Okay, so then let's look at the last one. So the third one, R3. So here for R3, what we have, we know for R3, the definition is A equal B or A equal negative B. So when we look at this, what we have, we will have this is whenever we have A equal B, it means the value of AB, of course, equal each other, right? So then when we flip BA, of course, if AB's value are same, then B also equal A. So that means, okay, for any same value of AB, we know AB and B are also in this. And then how about the other one? So now if we have A equal negative B, so for example, if we have 1 equal A equal 1, B equal negative 1, then what we will have 1 equal negative, negative 1, which is cancel, double negative will cancel each other. We will have A equal negative B. Okay, so maybe let's be happy here. So when A equal 1, B equal negative 1, we have our AB in this relation. And then how about our BA? So if we change the order of A and B, so we will have this is B on the left, this is B equal negative 1. On the right, this is negative A equal negative 1. So we have left is equal right. So then what we have, we will know our BA is also in this relation. Okay. So then what we will have, okay, when A equal 1, B equal negative 1, we have no matter AB or BA, they are all in this relation. However, we know now the AB's value are different, right? So this actually is a counterexample, right? So this is a counterexample because now the value of AB is now same. Okay. So what we know this relation is not anti-symmetric. Okay, so far so good. So this is a 3 example of what we have here. So we have this is we have two of them are anti-symmetric, but we have the third one which is not anti-symmetric. Okay, so then let's look a little more example here. So before I give you some more explanations, or maybe you can take a time and pause this video and think about, okay, is this 3, R4, R5, and R6, they are anti-symmetric or not? Okay, so you can try to think about this by yourself. Okay, so I hope everyone is pause this video and think this one by yourself. So now let's work this together. So for R4, what we have, we know the definition is just A equal B, right? So the definition is A equal B, and then what is if we try to find AB in this R4 relation, we will find the only case we can find is a value of AB are exactly same. So because of this, what we have, we will have, yeah, if the value of AB are same, then of course if we flip the order of BA is still in this one, and by this one we will know this actually is satisfies the requirement of our anti-symmetric because the value of AB are exactly same. Okay, so then let's move to the next one, R5. So for R5, the definition is A equal B plus 1. Okay, so now think about what is the value of A equal B plus 1. We can find many examples of AB in this relation. For example, if A equal 2, B equal 1, we will have 2 equal 1 plus 1. So which means this 2, 1 is in this relation. However, if we flip the order of A and B, this will become 1, 2, right? So now for BA as 1, 2, we know plug in this equation and change the order of our AB. The left will become B, which is equal 1. The right will become A plus 1, which is 2 plus 1 equals 3. So actually this BA as 2, 1, never in our R5 relation. So that means, of course, you can try more and more example, but actually we cannot find any example of AB and BA both in our R5 relation. So similar with our previous example R2, because we cannot find any example of AB and BA both in this relation, this means our definition of the anti-hypothesis, the anti-symmetric, the hypothesis is always false. So then by our knowledge in the logic operation, if the hypothesis is always false, then the conditions is always true. So based on this, we know, okay, we always satisfy the requirement of the anti-hypothesis. So because of this, so this is also an anti-symmetric relation. So this is again because the hypothesis is always false. Okay, so maybe let's rewrite this because we can't find any AB and BA in this relation. So the hypothesis the conditional is always false. The condition will be true. So this relation is an anti-symmetric relation. Okay. Yeah. So then let's look at the last one. The last one, R6. So R6, what we will have A plus B smaller or equal to 3. So now think about, is there an example of AB in this R6 and also BA in R6? So actually we have a lot of examples. So for example, we can have A equal 1, B equal 1, which is in this relation. And then we change the order of AB, so it's still 1, 1, it's still in this relation, and we have value of AB equal each other. However, if you think another example, for example, A equal 2, B equal 1, so we will have A plus B equal 2 plus 1, which means this is in our relation. However, if we leave the order of this AB, so then this will become A equal 1, B equal 2. So we have AB as 1 plus 2, smaller, which is smaller than or equal to 3. And if we talk about BA, which is as 2 plus 1, is still smaller than or equal to 3, right? So what we will have AB, BA are both in this relationship, but the value of AB are different. Both in relation here, both in this relation. Okay. But A, the value A and B are different. Okay. So what we have, so this relation is not anti-symmetric. Okay, because we find this counter example here. Okay. So far so good. So this is our explanation of several examples. We have 4 of them as anti-symmetric relation, and we have 2 of them are not. Okay. So then let's move to the next topic. So the next topic is the last relation we want, special relation we want to introduce in this lecture. So this is our transitive relation. So transitive relation is, again, we denote our relation as R, and this is a relation defined on our side A. So what we have if we have A, B, and B, C, both in this relation, then we should find AC. So it means that we link A, B, B, C, these two AC linked by B. So then we say, okay, if AC is also in this relation for all of the higher of the value in our side, then we say this is a transitive relation. And also, again, we can use our logic operator and the quantifier and sign symbol to guide this definition here. The hypothesis is two parts, AB in this relation and BC in the relation. And the conclusion is AC in this relation. And this is true for any ABC satisfy this requirement. Okay, so then again, I know this one is kind of abstract, so let's look at some example. So again, we use a similar example and let's check is this transitive relation or not. So for the first one, this is again A smaller or equal to B. Okay, so for this A smaller or equal to B, think about if now we have A is smaller or equal to B, B is smaller or equal to C, then do we have A smaller or equal to C? So for example, you can think this like if we have the value, for example, if we have A equal 1, B equal 2, C equal 3. So for here, we will have A smaller or equal to 2, which is 1 smaller or equal to 2, 2 is smaller or equal to 3. Then can we have 1 smaller or equal to 3? So of course, the answer is yes. Right. So we have AB and BC in this relation, and we also have our AC in this relation. So why we can have this? Because in our algebra course, we already know actually for the smaller or equal to, if we link this by a number in the middle, right? So then of course, the first one A will smaller or equal to the last number C. So that means actually for here, no matter what value we change for A, B, C, if we have our hypothesis, A, B, and B, C both in this relation, have this smaller or equal to relation, then we will have AC, it also have the relation as smaller or equal to. So that means for this one, we will have this is yes, this is a transitive relation. And then next we look at the second one. So second one is greater than. So for greater than relation, if we have A greater than B, B greater than C, then we have A greater than C. So again, this will use our knowledge in the algebra. So if you can think about A equals 3, B equals 2, C equals 1, and then of course you change any other example, satisfies A greater than B, B greater than C. So by our knowledge in algebra, yeah, of course, if we have both A, B, B, C in this relation, then we can have our AC is also in this relation. Okay. So based on this, we will, by similar reason, we can get our second relation is also a transitive relation. Okay. And then let's look at the third one. So for the third one, what we can have, we will have A equal B or A equal negative B. Okay. So here, what we can think, you can think also have some pi of AB in this relation or BC in the relation. So for example, if we have AB in this relation, it means one case, A equal B. The other one is A equal negative B. So if we have A equal B, and then we have another case like BC in this relation, so of course, because A already equal B, right? So if we have B, C in this relation R3, then because A's value of B are same, then of course our AC should also in this one. And then in the other one, if A is equal negative B, then what we have? So it's, for example, if A equal 1, B equal negative 1, we will have A equal negative B, which is double negative will cancel each other, so 1 equal 1. So now if A equal 1, B equal negative 1, and we have the case like BC is also in this relation. So it means, okay, so C is maybe in negative 1 or maybe in 1. So no matter what's the possible value of C, 1 or negative 1, we always have the A will in our equal C or maybe equal negative C. Okay, so think like this. So this is a little complete case, I understand it, but we just need to run in all of the possible case of this one. So here for this, let me type it here. So when A equal 1, B equal 1, or maybe or negative 1, if we have, then for us, we have AB in this relation. If BC also in this relation, we will find the only possible value of C is maybe also negative 1 or 1. But otherwise, BC won't in our relation R3. Okay. So because like the C's value is no matter it's negative 1 or 1, it's of course AC will also satisfy this also satisfy the requirement of this relation. So it's AC also in this relation, which means A equals C or A equal negative C. Okay. Yeah. So this is what we have here. So let me try to move this a little. Let's move back. Okay. So because of this, we will have our conclusion. So here we have AC also in this relation. So that means we will have this relation is also a transitive relation. Okay, so this is also correct. Okay, so far so good. And then again, now for the other 3 examples, so maybe you should pause our video first and think about this 3 examples. And do you think they are transitive or not? Okay, if you think it's not transitive, you need to try to find some counterexample by yourself. If you think it's transitive, then you think like all of the possible real number of AB. If AB, BC in this relation, can we also have AC in this relation? Okay, so how everyone is already think about this. So let's look at R4 together. So for R4, this is equal relation, right? So that means if we have AB in this relation, it means the value of AB are same. BC in this relation, it means BC's value have exactly same. So then if A equal B, B equal C, then just by our understanding of the equal relationship, we know, of course, AC equal each other. So based on this, we will know, okay, for this one, we also have, if we have AB, BC, both in this relation R4, we will have AC also in this relation R4. Okay, so then let's think about the next one, R5. So R5 is A equal B plus 1. So now if we think about this one, we try to find, is there some example, like for example, if we think about AB in this side, what we can find, we will have like, for example, A equal 2, B equal 1, then we will have AB in this relation, right? So because we will have 2 equal 1 plus 1, which make this equation whole. So you have AB in this relation. And then let's think about another one. So then for B equal 1, can we have some C here to make BC in this equation? So then we will like, okay, maybe like now we want BC in this relation, right? So what we think it means now the left-hand side should be B, the right-hand should be C. So it's in 1 equal our C plus 1. So that means here we should have C equal 0. Okay, then C equals 0 and BC in this relation. So then if we have this value of sighting, like A equal 2, B equal 1, C equal 0, then we have A equals C plus 1. Because now A equals 2, C equals 0. So we know 2 is not equal 0 plus 1, because 0 plus 1 equals 1. So that means by this one, although we have AB in the relation, BC in the relation, but our AC is not in this relation. So why? Because 2 is not equal 0 plus 1. Okay. So that means this is a counterexample of this one. So that means here we know this one actually is not a symmetric, it's not a transitive relation. So what we have, we know, okay, we find this counterexample, so it's not a transitive relation. Okay. Then similar for the R6, actually the conclusion is it's not a transitive relation. And then what we need to find, we also need to find a counterexample. So for this one, you can think like, okay, if we have AB in this one, so for example, we can have the value of A equal maybe 2, the value of B equal 1, then we also find a C. So for example, we can find C also equal 2. So what we will have, so for this one, we can write this counterexample as counterexample. So this is A equal 2, B equal 1, C equal 2. So for this one, we will have AB in this relation because 2 plus 1 is smaller than 3. And BC also in this relation because 1 plus 2 is smaller or equal to 3. However, for AC, this will become 2, right? So 2 plus 2 equals 4. It's now smaller or equal to 3. So that means our AC is not in this relation. So here we find this counterexample. So for this one, we will have this is not a transitive relation. Okay. So here in this video, I explained 2 important types of the relation. We introduced what is anti-symmetric relation. We also explained what is a transitive relation. I hope this is clear and this example can help you understand this definition. So thank you for watching this video and see you in next video.